Hello and welcome to Group 20 Spaghetti Bridge for Structures 1. The aim of the spaghetti bridge was to be the lightest bridge capable of supporting the greatest load. To do so, we had done some research to figure out what design would hold the most load. We had the idea for the base, however we were tossing up if we should do a Pratt or Warren style for the support beams. We landed on the Warren as the Pratt would support more weight and compression from above, however the weight was being tested from the base. In order to put that theory to the test, we started off constructing. We used the straw method which we found online to help stack the straws to create a thick base. So with little planning but big ideas, we assigned ourselves different roles to bring this bridge to life. However, there were requirements for the design of the bridge which had to have been met. For example, the weight limit was 200 grams and the length of the bridge had to have been at least 35 centimeters. And if you didn't know, the length of a spaghetti strand is roughly 25 centimeters. So in order for the bridge to reach that length, we decided to intertwine the spaghetti strands together, which in theory would be able to support the load. Before we knew it, we were gluing the base pieces together and suddenly it started to have a bit more structure to it. We did run into issues gluing the spaghetti together with flat edges. This had resulted in us creating a platform on top of the 5cm piece so it would hold it together. We didn't worry too much on the angle of the sides, however we very shortly realised a very big mistake. We made sure to take note and improve for future reference. However, even with the crooked angles, the bridge was finally coming together. And with that, our first bridge was done and ready to be tested. Yes, it didn't look like what we thought it would, with the Warren design falling through because of the weight of the bridge, the unique style of the angles, and not what a typical bridge would look like. But this bridge had taught us what we needed to improve in future, which was to plan 4 steps ahead with all the measurements and how it would support the load. It was all down to this moment. Would this bridge survive and keep our engineering hopes alive? Would all our hard work be for nothing?
It doesn't go any further.
Guys, we're trying to figure out how this works.
Can you push that button? No.
Okay, so it took us a couple tries to figure out how this machine actually worked, but we got there in the end. Now let's see that again to see what the weak points were in the bridge so then we can change it in our new design. The main weak point was the thickness of the base as it was a circular shape and only had one point of connection. This resulted in us changing our base design from having one point of connection to 4. However, this time we have them stacked on top of each other in layers to create a sandwich, and the joining point of each layer is connected at a different section. That way, when the weight pushes down in the middle of the base, it will be less likely to snap straight away as there are different weak points. So off we went again, gluing spaghetti together, then cutting and gluing and repeating this process. And after all of that, our base had finally come together. We had left the gap at the end not only for the outside support structure, but for the connection point to join the bases together, as you can see here. Now that we had the base done, it was time for the top. We had duplicated the same design from the bottom for the top, however, unlike our first bridge, we used trigonometry to calculate the length of the top to accommodate the side structures as if they were at a 75-degree angle. It was finally time to begin the process of constructing the Warren design. Although once we had finished all 4 corners, we decided to see if our calculations for the top were right, and they were not. We were off by less than 2 centimeters on each side. It was too late to change it, so we stuck to it, continuing with the wire and truss design. And just like that, we had finished our final bridge. Although the wire and design wasn't symmetrical, it was still beautiful. All that was left was to weigh it and test if it could support more than 3 kg. Luckily, the bridge only weighed 182 grams, so that requirement was a success. But now it all came down to this moment. Although the bridge didn't survive as long as we thought it would, it did beat our first design by 2 kg. Although it wasn't the winner overall and could definitely use some improvement, it was still the best bridge in our hearts. Thank you for watching us create our beautiful bridge, and maybe you'll see us construct more in the future.